Okay, hi everyone. Thanks for joining us today. Today we have Kristina Monsch from Smithsonian, and she'll tell us about connecting the dispersal phase to magnetic morphology-driven stellar spin down. Kristina, it's all yours.
Thank you. So thanks a lot for the introduction, also for inviting me to give a talk at your seminar. First of all, I would like to let you know I want to keep this very informal. So if you guys have any questions or comments, whatever, just feel free to interrupt me. We can discuss throughout my talk. Yeah, so I'm a postdoc at the Smithsonian. I finished my PhD like late 2021, so I still consider myself to be fairly new to the postdoc field. And I started my PhD actually working on exoplanet demographics, specifically on giant planet demographics and how these are affected by disk photoevaporation by the central star. And this is also how I got to work now on stellar rotation, because right now I'm very interested in investigating how the early phases of stellar systems, in particular when the star is still surrounded by the disk, is affecting the subsequent stellar spin down. So let's start with the standard picture, basically, of star and disk formation. I think you've all seen some kind of version of this plot. So in the classical picture, it starts with a dense or prestellar core, which becomes gravitationally unstable. And then the core accretes material and begins to collapse. And if the core has some kind of rotation, the low angular momentum gas will settle in the very center and then ultimately form a star. And around this, we'll have a massive dusty gas disk, out of which, which will surround the central star, and out of which planets will eventually form. And this is typically referred to as the class 2 and class 3 phase. And when we look at the frequency of circumstellar disks as a function of the age of a given region, so this is plotted here. So the disk frequency is a function of star forming region age. I think it's better to phrase it like this. We see that circumstellar disks are actually very short-lived objects. So for very young star-forming regions like Taurus or Orion C, we can see that disk fraction is almost like 80%, meaning that 80% of the stars in these regions are surrounded by circumstellar disks. But this the disk fraction decreases quite steeply as a function of age. So after 5 million years, for example, for Upper Sco, the disk fraction is already decreased to around 20%. And after 10 million years, most of the disks will have been dispersed. And this means that disks typically live, they rarely exceed lifetimes of 10, let's say, to 20 million years at most. So they are very short-lived objects. But even though they are short-lived, they can have a profound effect on the subsequent rotational evolution of a young star. And this is what you can see here in this plot here on the right, which shows the rotation rate as a function of age for a large collection of different open clusters, which are shown here as the black crosses. And you can see that these different regions span ages from very young, ages like 1 to 10 million years, up to a few giga years. And fast rotating stars are shown here on the top, meaning they have higher rotation rates, and slowly rotating stars are shown here at the bottom. And what you can see here is that young open clusters are born with a broad range of rotation periods. And during the time in which the stars are still surrounded by the disk, we can observe that the rotation stays more or less constant. But after the disk gets dispersed, the stars continue to contract, as they move forward to the zero-age main sequence, at which the hydrogen burning in the core will initiate. And from this point on, the stars will lose angular momentum and mass via an effect called magnetic braking. And at very late stages, we can explain their rotational evolution quite successfully with the so-called Skumenich law, which is an empirically derived law. And this is also the basis of the so-called gyrochronology, which enables us to determine stellar ages based on the masses and rotation period, of course. So the takeaway from this plot is that circumstellar disks break stellar rotation, so they keep the stellar rotation more or less constant. And even though, as I said, this is a very short time in the total lifetime of a star, this has some profound impact on the subsequent rotational evolution. So first of all, I want to give you a little introduction on how circumstellar disks disperse. So let's start with a very simple sketch of a young and active pre-main sequence star that is still surrounded by a massive circumstellar disk. So first of all, we know that these disks are viscous accretion disks. So mass is transported inwards, while mass is transported inwards onto the star, while angular momentum is redistributed outwards. And we know, however, that viscosity alone cannot be the main driver of disk evolution, simply because it would lead to significantly longer disk lifetimes than what we're actually observing. At the same time, we have, of course, planets that are forming in the disk, and they will also be altering the surface density structure, at least locally within the disk. And last but not least, the stars, of course, continuously irradiated. It's continuously irradiating the surrounding disk. And this is mostly via UV photons and X-rays, which will heat and ionize the upper layers of the surrounding disk. And the final dispersal of a circumstellar disk is then the interplay of all these different processes that act at different locations in the disk with different time scales. And while the disk will spend most of its lifetime during this relatively low phase of viscous accretion, it will get dispersed very quickly once it reaches the final stages at which the stellar irradiation becomes important. So, as I was saying, this energetic these energetic photons that are emitted by the host star, they will heat and ionize the upper layers of the surrounding disk. And at some point, the gas in the disk will become unbound near the so-called gravitational radius. And from this radius on, the gas is removed by pressure-driven disk wind, and therefore a gap is opened so that the inner disk is cut off entirely from the outer disk, meaning that there's no mass supply possible from the outer disk anymore. And while the inner disk is then viscously, sorry, I lost my animation, but the inner disk will be viscously drained by the host star. And while this is happening, the central star will also directly irradiate the outer disk so that it becomes very efficiently heated and removed in a matter of a few 100,000 years. And this is the so-called, or this leads to the so-called two timescale behavior, which means where we have a very long, as I was saying, very long phase of viscous accretion, but as soon as gap opening is happening due to photoevaporation, the disk is dispersed very efficiently on a very short time scale. And this plot here shows the mass loss rate as a function of time, both for the viscous accretion rate, which is shown here as the black dashed and dotted lines. And you can see that this is the function, for the viscous accretion rate will decrease with increasing age. And the different lines correspond to different disk configurations. And the orange lines, they show the wind mass loss rate due to the photoevaporation coming from the central star. And these basically, so this mass loss rate basically stays constant throughout time, because also the stellar irradiation stays constant throughout the same. And basically for every disk configuration, you can find a time at which the viscous accretion rate will fall below the wind mass loss rate. And this is then when photoevaporation starts to dominate disk evolution, and therefore the gap will open within the disk. Oops, yeah. And this video here shows you, so this video shows you basically an example of how this would look like for disks. So the y-axis is this 1D surface density, and the x-axis is the radius of the disk. And I'll talk in a second about these different lines, but they're basically all showing the same behavior. So you have a relatively long phase of viscous accretion where the surface density is only decreasing steadily, but at some point the viscous accretion rate will fall below the wind mass loss rate. You have the gap opening here, and then the remaining disk will be removed on a very short time scale, typically, as I was saying, like a few 100,000 years. And yeah, so the details about the dispersal process are, however, also very important. And we know, so I want to explain to you now what these different lines are showing. So we know that a star is not only irradiating X-rays or EUV, but it's like a spectrum of all kinds of different wavelengths. So we have the FUV, the EUV, then the soft X-rays and the hard X-rays. So also here it's like a combination of different photons with different energies that will be contributing to the heating of the gas in the disk. And actually it makes a very big difference on the mass loss rate you obtain for photoevaporation profile if you assume different photons for your models. So I want to explain this a little bit more. So this plot here shows the normalized mass loss rate for these three different photoevaporation profiles as a function of disk radius. So the green curve shows let's start with red. Red is far ultraviolet. These photons are less energetic than 13.6 eV, meaning that they are not energetic enough to ionize hydrogen, but they can dissociate hydrogen molecule. While UV photoevaporation is dominated by extreme ultraviolet photons, which have energies that are enough to ionize hydrogen atoms. But this also means that they, while this is a very efficient heating mechanism, these photons can penetrate the disk very deeply because they are absorbed very efficiently by the hydrogen in the disk. And soft X-rays are energetic enough to ionize and penetrate the disk relatively deeply. And therefore, X-ray photoevaporation is a very efficient mechanism in order to heat the disk and therefore remove it or disperse it in timescales that we're actually observing. And this is mostly because of the penetration depth of these different photons. So as I was saying, UV photons cannot really penetrate the disk very deep, while X-rays can penetrate it very much more deeply and therefore heat it more efficiently. And therefore the mass loss rate, as well as the location of the gap opening due to photoevaporation, depends very drastically on the photoevaporation profile you assume. And my group in Munich, while I did my PhD, was very active in developing this EUV plus X-ray photoevaporation model. Even though there are different flavors of photoevaporation models and also different opinions on the efficacy of these different models. But I've been working a lot with the X-ray photoevaporation model, which I'll be talking about now. So this is just like for you to more or less understand the workflow of photoevaporation models, but I won't be going too much into detail here because this is not my expertise, unfortunately. But basically what you do in order to develop a photoevaporation model is that you or what we did is that we coupled hydrodynamical calculations, and for that purpose, we used Pluto, and these were coupled with 3D radiative transfer models. And these are not coupled on the fly, but what you do is that you get a prescription of the temperature in the gas as a function of ionization parameter and column density that you can put into your hydrodynamical calculation. And then you basically run this disk system, wait until you reach a steady state. And if you then integrate the streamlines from the wind, you obtain so-called mass loss rates and radial mass loss profiles, which is basically just an analytic function that can, or that tells you how much mass you'll be removing in the disk at a given location per unit time. And this is then a very easy way to implement this into 1D viscous evolution code, which was specifically what I was mostly working on during my PhD, where I investigated how photoevaporation is impacting giant planet migration. And yes, you can also obtain observables like disk demographics, synthetic line profiles. And yeah, the main result from these photoevaporation calculations is basically this plot here on the top, which is the surface mass loss profile. So it's the, as I was saying, the mass loss per unit time, per unit area, as a function of distance to the central star. So it basically tells you how much mass is removed where in the disk. And these different lines show different profiles for different star system models. So our current grid ranges from 0.1 solar masses all the way up to 1 solar mass. And this photoevaporation model is very successful in reproducing key key properties of protoplanetary disks, such as the disk lifetime. So the this is here shown on the top. So I've shown this disk fraction versus age plot earlier. So the two different lines here are two different X-ray photoevaporation models. We can talk about it later if you're more interested about this. But we can successfully recover this characteristic decline of disk fraction as a function of age, but we can also reproduce substructures in transition disks like cavities and gaps that are observed. And also here we're successful in reproducing many of the observed transition disks. And yeah, so how do we all connect this to stellar rotation now? Basically, what we want to obtain is analytic prescription of the disk lifetimes as a function of the stellar X-ray luminosity and stellar mass. And this is so you get this very easily from our photoevaporation model because it uses the X-ray luminosity and the stellar mass as an input. And this is shown here in the left plot. The top panel shows the X-ray luminosity of the star as a function of stellar mass, and the colors correspond to different disk lifetimes. So light is very short disk lifetimes, and dark blue is long disk lifetime. Long means like 10 to 20 million years. And you see that for high X-ray luminosities, you get short disk lifetimes, while for low X-ray luminosities, you have longer ones. And higher stellar masses tend to have longer lived disks than, sorry, it's the other way around. But before I'm confusing myself, the main effect of the disk lifetime is, the disk lifetime mostly depends on the X-ray luminosity. You have a 2D dependence, but the dependence of the X-ray luminosity is much stronger than it is on the stellar mass. And the bottom panel shows you then the disk lifetime as a function of stellar mass. the blue line is what we get from the model. And the black crosses, they show observational data points from Lambda Ori, which is a 5 million year star forming region. And we can see that so we can easily reproduce the observed disk lifetimes in this region. And therefore we get an analytic prescription that just uses stellar mass and X-ray luminosity as an input. And from this, we can calculate disk lifetimes. And luckily, we have both quantities available also from observation. So there are several very deep X-ray surveys available of young star forming regions. So we know how the stellar X-ray luminosity correlates with stellar mass in these regions. I hope you can more or less see this on these bottom plots here. So basically this shows the X-ray luminosity as a function of mass for the ONT here on the left and for the Taurus star forming region on the right. And basically by knowing how the X-ray luminosity correlates with stellar mass, you can use realistic input properties for stellar rotation models and calculate self-consistently the disk lifetimes from that. So now let's finally talk about stellar rotation. So how do we connect the dispersal phase to the stellar rotation evolution? So these two sketches show the internal structure of a fully convective star here on the left and a partly convective star here on the right. So low mass stars have convective envelopes, and these generate magnetic fields under the surface. And the faster these stars rotate, the stronger these magnetic fields are, and also the magnetic activity becomes. But also magnetic activity controls stellar rotation and through magnetic braking. So stars that have a magnetic field develop magnetized winds so that the plasma, instead of leaving the star at the surface, will follow the magnetic field lines and essentially co-rotate with the star at much larger distance. And that provides basically a lever arm that makes magnetic braking a very efficient way to spin stellar rotation down. And this is why especially cool stars spin down very rapidly. So rotation fuels activity and activity controls rotation, meaning that this is a self-regulating mechanism. And this has been also observationally established in this rotation activity relation that can be used in order to connect stellar activity with stellar rotation. And from this, we also know that rotation and X-ray activity are tightly coupled. So, and in particular, I am working with the stellar rotation or stellar spin down model by Cecilia Garofalo, which she presented in her 2015, 2016, and 2018 paper. So we know that, so typically it's assumed that young stars or stars in general have a dipolar magnetic morphology, but this is actually not the case. So observations of young star forming regions have shown that young stars can actually have higher order magnetic fields or magnetic field morphologies, to be more precise. And this is how these maps would look like. So this is these are typically mapped by using a ZDI map. So a dipole, so you see that the dipole looks quite different from a quadrupole, and the substructure becomes more you see basically more substructure in these ZDI maps. And this is from these synthetic ZDI maps, just to show you how these would look like for different magnetic morphology. And as I was saying, recently there has been more and more observational evidence, or in general more observations of these geometries of young star or of magnetic fields of young stars. And Cecilia was using these as an input to her stellar rotation model. And what she found is that the angular momentum loss can be drastically reduced if you include higher order magnetic fields into your stellar spin down calculation. So when you start with a dipole, which we define as n equals 1 in these plots, and go then to a quadrupole, you can almost get a decrease of 1 order of magnitude in angular momentum loss rate, meaning that the higher order the magnetic field, the less efficient the star will lose angular momentum. And this is directly connected to the open flux that we can measure from these stars. And this is because, or this is demonstrated here in this plot on the bottom. So this shows the open, or the magnetic field lines for different configurations of stellar magnetic fields, so dipole, quadrupole, etc. And you see that for dipole, you have a larger amount of open field lines. Basically, I'm just showing the closed field lines here, but if we include also the open field lines, you see that the dipole has a larger number of open field lines, and therefore it can lose more angular momentum, while with higher magnetic, with higher order of the magnetic fields, you get more and more closed field lines, meaning that the star can or becomes less efficient in losing angular momentum and mass. Yeah, and when you look at how this affects stellar rotation, it becomes apparent that, so when you just look at the classic dipolar magnetic field, you see that these different tracks, so if you look at the rotation period as a function of h, and start with different initial rotation periods, after about 100 million years or so, all of these different tracks will converge to this one empirical, or like this one track, which is the Skumanich branch that I was talking about earlier. And this is solely mass dependent at some point. However, if you include higher order magnetic fields, you see that these different tracks only start to converge after around 1,000 gigayears. Sorry, 1,000 million years, so 1 gigayear or a few gigayears. And before that, you have a strong, or you can develop a strong bimodality in rotation periods, depending on if the star was initially fast rotating or slowly rotating. And this means that this shows that the increasing magnetic complexity strongly reduces angular momentum loss rate. And this can very well explain what we're actually observing. So as I was saying earlier, so young star forming regions are born with a broad range of rotation periods, but relatively quickly you will see a slow rotator sequence that is developing typically so we can see it already quite well in Pleiades. And you also have, however, a sequence of fast rotators that models had trouble explaining. And yeah, maybe it's better to show it here on the plot on the right, which is a very recent compilation from Curtis 2020. So let's start maybe from the youngest region. So Pleiades are the blue data points. You see the slow rotating sequence, but as well some fast rotators. And then with increasing age, this bimodality vanishes. So you only end up with the slow rotator sequence, which is successfully described by the Skumanich law. But rotational spin-down models had a great difficulty in explaining this bimodality. So how can we have fast and slow rotating stars there at the same time? As I was saying, Cecilia's model that includes higher order magnetic fields is very successful in doing this, because we know how the magnetic complexity varies as a function of stellar Rossby number, which is rotation period divided by the convective turnover time of the star. And this is just a law that, or just a relation that Cecilia has derived. It's not necessarily that this relation has to look like this, but this relation was very successful in reproducing the observations. And then we use convective turnover times, moment of inertia, and in general stellar properties from stellar evolutionary tracks, in particular the mist models. We can feed this into the stellar spin-down model. And in the end, we get a huge grid, so rotation period versus age for different stellar masses, which are shown in the columns. And we see that the stellar mass mostly, I mean, it's probably a bit hard to see because there's so many panels here on the slide, but the stellar mass mostly, as I was saying, affects the final rotation period to which these different tracks will converge to, which is the Skumanich branch. But the disk locking time will affect, which is shown in the rows of this plot, determines how many stars end up in the fast rotating branch and in the slow rotating branch at a given point in time. And we can then use realistic input conditions and test how this, or if we can reproduce observed rotation period distributions using our model. So here I was using the ONC as an input. I used the rotation periods from ONC, and I calculated the rotation period as a function of stellar mass and extra luminosity from that region. So I could calculate the disk lifetime, but just as a proof of concept, I was first assuming constant disk lifetimes, which is typically done in these stellar spin-down models. So this is again rotation period as a function of age, and these different, so the different colors from the blue lines correspond to different stellar masses because I'm trying to model the entire population in the ONC. And these vertical lines here show the rotation period distributions of selected open clusters. So orange is, for example, H per, then red is Pleiades, and we have Praesepe and Hyades in here as well. And if we assume a constant disk lifetime, which was here 13 million years, which is the same age as H per, we see that we cannot reproduce the entire range of rotation periods that is observed in H per. So we would either have to go or have to increase the range of rotation periods in order to be able to explain all of these stars, but then we would end up with many stars that exceed the breakup rotation period and would thus basically fall apart, right? And we would end up with way too many fast rotators. But also 30 million years is a relatively long disk lifetime, as I was saying earlier. So disks rarely survive much longer than 30 million years. So it's safe to assume that most disks will actually have much shorter disk lifetimes. So that's why the second test was to use 5 million years as constant disk lifetime, and we already do a better job. So I'm going between both plots. So we already do a better job in reproducing the fast rotators, but it's still not very good for the fastest rotators. But also here at later ages, like Pleiades and Praesepe are already better reproduced. However, if we use then this variable disk lifetime model in which we calculate the disk lifetimes self-consistently based on the stellar mass and rotation, stellar mass and extra luminosity, we can very easily reproduce the entire range of rotation periods that is observed for H per. We also recreate the entire range of rotation periods for older stuff, open clusters. However, of course, our model is not perfect yet. So at this point, we still end up with too many fast rotators at late stages, meaning our model is very successful in producing this bimodality of rotation periods at late ages, or let's say between 100 and 1,000 million years. And this is something we have to still work on. But if we go to, so if we, for example, test Taurus, because ONC is a, let's say, very special star forming region because it's it has lots of massive stars, right? So you have a strong UV radiation field. But if you go to a more low mass star forming region like Taurus and do the same thing, we more or less obtain the same result. And what we can then do is to compare our model results to actual observed rotation period distribution. And this is just a histogram of the distributions from these regions I was showing you earlier here, compared to the models for the ONC and Taurus. As I was saying, we still overpopulate the amount of fast rotators. However, we are very successful in producing this bimodality at all, which many models are still struggling with. We can also look at 2D space, so rotation period versus mass. And again, the bimodality is recovered easily, but there's still some work that needs to be done in order to explain the details of this plot, especially, for example, if you go to NGC 6811, which is around 1 gigayear old, you see that this branch, or that our model does a quite poor job in reproducing this low rotator sequence, while for M37, for example, it fits basically perfectly. And this is the so-called stalling that has been recently observed, but it's not clear yet what is producing the stalling of low mass stars. So why these stars tend to slow down more slowly than what we would expect from SCU-manage. And then, as I was saying, our model still doesn't perform perfectly. It's quite good, but it doesn't perform perfectly. So we can use, by comparing the model to observations, we can calibrate our model. And this is partly also what, I forgot to put the reference here, but it's the Gossage 2021 paper, where Sask was deriving a different relation of stellar magnetic complexity as a function of Rossby number. And this way you can easily calibrate your model in order to reproduce the observation better. And ultimately, what can you do with all this? So of course, we need to understand stellar rotation in order to perform gyrochronology, for example, in order to know stellar ages. But I am particularly interested in connecting stellar rotation to the stellar X-ray luminosity. So as I was saying before, stellar activity is strongly correlated with stellar rotation. And by using this rotation activity relation and our model, we can obtain prescriptions on how the X-ray luminosity is evolving as a function of age. And this is this knowledge can be used actually for lots of different topics within the field. So first of all, for example, for this Kepler radius value, which I know you guys at Caltech are working a lot on. So it's the scarcity of planets with radii between 0.5 and 2 Earth radii. And there have been basically two leading theories in what could cause this radius valley. And one of this is PHOTOEVAPORATIon by a central star. And however, we need to understand how the stellar X-ray luminosity is evolving as a function of age for this, because we know from observations that the stellar X-ray luminosity actually decreases by up to 3 orders of magnitude within the first 1 or 2 gigayears of the stellar lifetime. But also you can use it for inferring or understanding giant planet demographics, which was specifically what I was working on during my PhD, where I was interested in understanding this pileup of gas giants that we're observing close to 1 AU. And this PHOTOEVAPORATIon by the central star is actually very successful in explaining this pileup of gas giants at around 1 AU. And I was performing some numerical calculations during my PhD, and also gathered extra observations of planet hosting stars. But these are at the order of gigayears, while my models were performed at the order of million years. So we need to understand how the stellar X-ray emission is evolving during these two different stages of stellar evolution in order to really understand if photoevaporation is indeed the underlying mechanism. So yeah, this is basically what I'll be working on next. And I've summarized the main points of my talk in the slide here. And yeah, I'm happy to take questions, and yeah, thanks a lot for having me.
Thanks for the talk, Kristina. So in the audience, online or here in person, please ask questions. And yeah.
Yeah, I have a question. When you were modeling to reproduce the data of the evolution of the rotation period as a function of mass, how much have you played with the initial conditions of that model, or of the initial rotation periods? Because it sounded like some of those fast rotations could be reproduced also by changing the initial conditions.
Sorry, let me just go back to my screen. Oops, sorry about that. I accidentally pressed the wrong button. Yeah, the initial conditions actually play a big role. So what I tried to do back then was to use simply realistic input conditions. So that's why I was using properties from the ONC in Taurus. So I was taking the initial rotation period distribution, actual luminosities and stellar masses from the data and tried to resample. So I increased I obtained a synthetic data set that was sampled from the observational data set. But I played around with the initial conditions in terms of initial rotation period, but we cannot really extend the range much further if we want, because if we include two, so if the range is too broad, so if we have more fast rotating stars here, for example, many of these stars will break up at some point. So and the MIST tables that we're actually using at this point don't treat. So we're calculating the rotation self-consistently using the spin-down model, but the MIST tables wouldn't tell us basically that these stars are broken up and unphysical. So the MIST tables actually would still be included. So that's why we have to manually exclude them from our model. And that's why I try to stay within observed ranges of initial rotation periods. I mean, I don't know which other initial conditions maybe you are thinking about that we could play around with rather than rotation periods.
No, that was my question. Thank you.
Okay. So maybe I can add. Sorry. Yeah. Sorry. No, go ahead.
In the audience, online. Yeah.
I'll jump in with one. Yeah. What do you make of the X-ray luminosity differences between the stars that still at the same age, at the very young ages, the stars that still have distances that don't? Like
so you're referring to this plot here, right? Yeah, sorry, I didn't explain this actually. So these different lines show the models for different initial rotation periods. So the yellow line is a more slowly rotating star, while the dark line is a faster rotating star. And since rotation and activity are correlated, these stars with slower rotation will have lower activity and therefore lower axial luminosities. And this is basically what you see in this plot. And the dotted line here, the vertical lines, they show the disk lifetimes for each respective track. So the star with slower initial rotation will have longer disk lifetimes than the star with faster initial rotation. And this is then also what you see in the cumulative X-ray luminosity as a function of age. So which is basically the total dose of X-ray emission that will hit, for example, a planet, or which is just emitted by the star. And you see that for a fast rotating star, the total dose of X-ray emission will be much larger, by a factor of 2 almost, compared to a star that is initially slowly rotating. Yeah, thanks for pointing that out.
Not at all what I was asking.
Any last question for Kristina? Yeah, if not, let's thank Kristina again.
Yeah, thanks a lot.
Okay, thank you. And
Good,
we'll
then.
end here.